So don't be allergic to equations. No, difficult. It is there. You'll have to. Once you get the equation, your PhD is very fast. Your supervision is very simple. Now it is very easy. Students can find it out for you. But you'll have the final judgment should be with you, whether you should allow him to use this equation because he doesn't experience. Whether it will work or not, even by intuition you should guide him, but don't force him, because he may be right, you may be wrong. So there should be always an escape route. Hey, I think this equation is good, but if it doesn't work, use the other one. Don't insist. Then you will be intelligent, but you will not wise. So try to be wise as well. So in extrusion mechanism, some more details here. Okay, very close to the cutting edge, as you set your depth of cut, this is the line, and in this region, severe plastic deformation takes place. Okay, below that is the elastic deformation zone. Spring back returns the material, but some of the material, when from this region, flows below the cutting edge, and what going out is chip. So, and chip curvature takes place here. These are the boundary line for elastic plastic deformation. This is the boundary line for deformation constraint, and here elastic deformation takes place. Some of the material escapes. Okay. So all these different zones have been named. You can see in the slides. I need not go into the details. Okay. Now, as you have seen in the previous slide also, as your chip thickness becomes thinner and thinner as you go down, your specific cutting energy increases drastically. Okay. So exactly what I answered the question yesterday. As you go for very high speed machining, and you are not actually removing chip, you are rubbing and you are spending energy for just increasing specific cutting energy. That's all. Okay. So up to you whether you will go for unnecessary high speed or not. Okay. Microstructure effect. Now here comes, when your chip thickness is large and whatever boundary condition is there, fracture may take place along that line. But when your chip thickness is very small, then your compression is large. I will come to that next presentation. Your compression is large enough and you do not allow the material to break along their boundary line. You suppress them. That's why extrusion takes place. Remember that. In extrusion, compressive stress is larger than your tensile stress. So this is the basic condition. Is it clear? So you'll have to have, even for, now very quick hint, in brittle material what happens? Brittle material usually fractures because of tension. And if you can suppress that, then you can avoid that breakage and compel it to come under plastic deformation. But there is a limit for that. I will discuss all this when I go to next one. Okay. Now, same thing. Actually, this extrusion mechanism is our journey now. Whether it's for ductile material or brittle material. And for ductile material, limit is very large. For brittle material, limit is very small. God has decided the limit, and we cannot control it. Okay? That is the only difference. And molecular dynamics, again, it has been proven by molecular dynamics modeling Again, you will have to go through this formulation, deformation at atomic scale, atomic behavior versus plastic flow, a potential energy function for Newtonian mechanics. So I'm not going to drag into that one. Just when you try to do molecular dynamics analysis, you'll have to consider those. For that, you bring in the equation and solve it. Okay? It was done long time back when the first diamond turning machine was developed in USA and the Lawrence Liverpool National Laboratory, and this analysis was done by Professor Ikawa in Japan, long time back. And we published a paper, you can refer that paper as well, but I'm not going to elaborate on it. And all these equations they brought in, Morse potential E, which is elastic modulus, interatomic distance, cohesive energy, all these were considered. And for copper, copper material to material combination, and then tool and workpiece contact, these were considered. I'm not going to go into the details of it, but basic things, if you want to do molecular dynamic analysis, you'll have to consider those things. Okay? Now I think you got some hint. You yourself can do ductile mode machining of brittle material as well. Do I need to elaborate on it? Let me go. From now on, I'll talk about ductile mode material of brittle material. The story I have told my Pakistani student how he objected, but he did it nicely. So, ductile mode machining of brittle material, a special application of diamond turning on brittle material where material removal is performed through dislocation or plastic deformation rather than crack propagation. Remember that. If it is crack propagation, then brittle material will crack and fracture. It will be abrasive machining or fragmented machining, machining brittle material in brittle mode. Then you need to force it, you have to change your boundary condition to bring it to ductile mode. That means you are not allowing the fracture to take place. Before that you are deforming the material. Okay? Or you are delaying the fracture, and by the time you finish your machining. Basic thing is that. Sorry, let me go back. So comparison between brittle and fracture material. Brittle fracture. In ductile machining, easier to control the process. If you can keep it in the ductile mode, it is free from cracks and you can get smoother surface. So for that, people are doing ductile mode machining of brittle material, not knowing the mechanism not knowing the theory behind it. And we started, luckily, I got a paper published by Dr. Lon, and from there we reinvented or invented the wheel which was there but nobody invented it. So all these were there. This research was done in 1995. What they did, you look at it. It is a diamond turning machine and there is a tool with big nose radius. Okay? So what they did, they started plunge cutting. And what they did, initially the feed rate was very small. Slowly they increased the feed rate. And finally when feed rate was large, the fracture started. So the feed rate played this important role, which I will show you later in milling case of silicon. By changing the feed rate, how we controlled from one, for silicon, critical chip thickness should be 1 micron. From there, how we got into the depth of even 0.5 millimeter. Okay? It played with feed rate. So all these references helped us, but this paper was, we found it later, but when Arif, my student, did it, he intuitively thought that if I change the feed rate based on the equation, then we can do it. I'll come to the details later, okay? So this one, I don't know whether I should elaborate further. As you increase your feed rate, then you exceed the critical zone, critical value, and you end up getting it. So this is the example. Now, these are the few factors you should remember. So what he's using, he's moving from here to there and increasing the feed rate and to get 100% ductile regime when the depth of damage YC. When you see, it's reverse case is milling. Here, in reverse, as in milling, if you consider it as milling, if you take up milling, and this is the case, you are increasing the feed rate here, because in up milling, critical chip thickness changes. Here you are intentionally changing the chip thickness. Okay? So whichever conveniently you think, you can think of up milling, you can think of plunge turning. So as you increase your chip thickness, your radial depth of cut increases, and the cracks generate at critical depth of cut. They did not know that there is a value which is critical chip thickness, but we finally found it in a paper. And for silicon, that critical chip thickness is 1 micron. For tungsten, it is 3.5 micron. So they machined silicon, and at that point, the crack generated. Now this crack, if it is your bottom surface is here, then this crack, or move the bottom surface here, and if the crack reaches the bottom surface, then the whole surface will be full of crack. But if the crack generated does not go very deep, it remains here somewhere, then you are safe. In milling you can control, here they could not control. So that way he found that there is a critical chip thickness, critical feed rate, which, and again, nose radius comes in the picture. I'll show you an elaborate picture. So that is the thing. In brittle material, you'll have to control the feed rate and depth of cut very carefully, then you can machine brittle material. Is that, I'll show you later that their compressive stress is so large, fracture is taken over. So it doesn't allow the fracture to take place. And Scattergood developed this equation, and this equation is interesting. If you look at the previous thing, all these values are there. Z effective, YC, depth of cut, D, chip thickness, A, all these feed rate, all these things were there. Based on that, he developed an equation, which is, what equation it is? It is a geometric equation. It is not mathematical equation. Mathematical equation, but based on geometrical terms. All right? So once you know all the geometry, you put them in equation, that is also possible. Partly it is empirical, but definitely it's a good approach to solve geometrically. So there are different types of equations. Okay? And then also here, he didn't do finite element analysis. You can predict all the values if you carry out finite element analysis based on this geometric equation. Yes. Yes, please.
Excuse me, sir. Sir, in ductile mode machining, when we reduce the uncut chip thickness below the critical chip thickness, so how do the brittle material changes into the ductile behavior?
Yes, material doesn't change.
Yeah,
your cutting zone behaves as ductile zone. Is it clear?
Yes.
Brittle material is brittle material.
Yes.
Depending on how you are going to do the machining.
Okay.
Are you suppressing that so that brittle fracture cannot take place, and this is controlled by the chip thickness.
Okay.
Then you are in ductile mode. You are machining the material in ductile mode. If you increase your depth of cut or feed rate too much,
okay,
then you are machining brittle material in brittle mode.
Okay. So this critical uncut chip thickness will be always less than the minimum chip thickness which is required for the chip formation. So the most probably the cutting mechanism will be the plowing mechanism.
Cutting mechanism will be?
Basically predominant will be plowing mechanism, isn't it, sir? Plowing.
Oh, plow. No. Don't say. Plowing is different thing.
Okay.
You are dragging me to Merchant's equation. No. I'm not talking about. This is extrusion. This is extrusion mechanism. I'm still in extrusion mechanism.
Okay.
Because my starting point was there. My starting point is here.
Okay.
Extrusion mechanism. Then you go to here also extrusion mechanism. The top one is fracture mechanism. The bottom one, chip thickness is so little, it is extrusion mechanism. We are in the extrusion mechanism. Okay? Plowing is another thing. Plowing, even if the chip thickness, usually it is a very, very thin chip, plowing takes place. Plowing is below the extrusion zone.
Okay.
Yeah, below the extrusion zone. Okay, so this is geometrical equation based on which he came to this, what should be the maximum clean area without any fracture. That is that effective. So, okay. So I think I should not elaborate on all the terms are given here. Why should I dwell on somebody else's equation? It's fine. The notes are there with you. And he showed experimental results, he analyzed from the edge. As you move in, you see the fine feed slowly increases feed rate and fracture comes in. Okay? Critical tool feed up to here, after that it cracks. Okay? And look at the chips. When you are in the ductile mode, continuous chips produced during ductile mode machining of brittle material. And dislocation chips comes up when you exceed the critical chip thickness. Clear? So this is ductile mode machining of brittle material. It is brittle mode machining of brittle material. All right? And again, when you can consider is tip edge radius here, edge radius, nose radius all comes in. When tool edge radius is 23, which is R, and feed rate, let me see, feed rate, micrometer per revolution, depth of cut is A, take the ratio of A by R, and then tool edge radius 23, you can have higher edge radius, and same cutting speed. That feed rate you vary here. Feed rate you vary. Then you see the behavior, experimental results. Okay. When your tool edge radius is 23 and maximum thickness is this much, you can get very fine surface. But as you increase your edge radius to 202 and you increase your uncut chip thickness A, then you get fracture. You can have higher edge radius, still you can get surface, but you increase your uncut chip thickness, you get fracture. But when you reach the ultimate, if your tool edge radius is very large and uncut chip thickness, for any uncut chip thickness, you get fracture. So then, that means if your edge radius is extremely large, you spend too much of energy to take care of specific category energy and end up getting fracture. So you'll have to play with this parameter very carefully. So here I stopped for extrusion mechanism. Any question? Clear? Yes, please. No question. Yes.
You have shown there is an effect of feed also. So is there any term of critical feed in case of brittle material machining?
Okay, critical feed, I'm coming in mailing, I'll show you. When feed is too fast, then you reach the critical chip thickness very fast. Okay? Then you get fracture.
That is true for milling, but in case of
the same thing applies in, you take the, I showed this example, when your feed rate is very large, then this example, I hope I can clear it here as well. And when your feed rate is very large, what happens? This line comes down. If it comes down, the crack, the moment crack generates, it touches the surface. So you get fracture. Whereas, if you reduce your feed rate, imagine, if you reduce your feed rate, your crack generation moves up. So it cannot reach the surface. So very large feed rate is dangerous. Small, always smaller, the better. Then if it is too small, you can get higher radial depth of cut, but your material removal rate, you need to calculate. If your depth is too large, then your feed rate is very small. You'll have to calculate which way you get maximum metal removal rate. Increasing feed rate, you go it fast. But increasing feed rate, danger is that crack will generate. Rather than increasing feed rate, you would increase your cutting speed. Increase your cutting speed, reduce your feed rate, that may give you much better metal removal rate. This is simple calculation you can do and find out which is better.
Yeah, I mean, to just add to it, the feed rate is not going to change your critical chip thickness. It is not going to change the crack length.
Yeah.
What is taken care that where this critical chip thickness, if you look at the geometry, as I said, is more of the geometrical analysis.
Yeah.
So if it's just like solving a puzzle, where this critical chip thickness will occur. If you have a feed rate, if it moves up, so it is not going to change the critical chip thickness. It is not going to change the your crack. Only thing is that, are you bringing it down or making it up? So cracks will be there, but they will be taken away by the chips. That's it.
In the next cut, the crack surface will be removed. So long it doesn't touch the baseline, you are safe. But never try to play exactly touch point. Leave enough allowance so that you are always safe. That's the thing. So these are basically how we'll think to get a safe zone. That is individual's credit. And because all these things are all there, you can calculate. To get this that effective, what you need to change, how need to change. Some things, the R value, radius value, sometimes it comes in square root. So you'll have to see how it affects. Okay, now yes.
So you have shown that as we change the tool edge radius, the maximum undeformed chip thickness increases and brittle fracture takes place. So how we measure the edge radius?
Edge radius. Elegant.
Sir, how they have varied, like from 23 nanometer they started and they lasted at 807 nanometer. So how we vary it, like it's for the same nose radius? Sir, how?
Yeah, okay, I got it. How will you, sorry?
How we will vary the edge radius?
Yeah, you will have to get it machined by, not by you, but by the manufacturer. You will have to assign the duty, because once you get the edge radius, a certain value, then what I know, they got continue to lap. If you lap your rake face, you lap your clearance face, your edge radius is changing.
But sir, nose radius will remain same.
Nose radius also, you can play with nose radius, and if you have
The study, sir, you have shown it is for a constant nose radius, but edge radius is changing.
Okay, you can change the nose radius also depending on to improve the surface finish. Shall I show you that? If you edge radius, nose radius is large,
Then we get a better surface quality.
surface finish. If you want to change that, that also will have to give it to the manufacturer to change your edge radius, nose radius. They can make tools with different nose radius.
Okay, sir.
Yeah. If you try to do it by ourselves, it is quite difficult. Possible, but then you spend energy for something which somebody else can do for you. As a supervisor, those who are supervisor, my honest request to you is not to do the job, but to get the job done. Please never ever try to do any analysis for your student, because that way he loses his interest. You are not creating interest in him to do work, and you are tired. This guy is very poor in analysis, I will do it. No, never do it. Most important task for you is to give the spark, to get inspired to do it. Okay? Luckily, just a side talk. I never thought what is the meaning of my name. Yes, you want to say something?
No, sir, please.
I never thought what is the meaning of. I know that Mustafizur, Rahman is God, Mustafizur has a meaning. And when I went for Hajj, I met an Iraqi guy. So he said, sir, what is your name? This. Do you know the meaning of your name? I said, yes, I know. Meaning actually is to inspire people to follow God, not to be on his own. Inspiring people to follow God, and to obey God. He said, no, sir, your name has two meanings. One is agitator, another is inspirer. Then I thought, how one name, two meanings? I was really, when I wanted to go for politics, I was a student leader, I was the general secretary of University Students' Union, and so I was always agitating the students against the admin. But I was doing good compromise between two. And of course what I do nowadays, Afzal is witness, I try to inspire them, tap them always and tell them and inspire them. So your responsibility, all of you should try to inspire, never ever scold any student. Never ever try to lose your temper. That will show off, demoralize the student. I don't know whether you feel it or not. Good students respects to teachers a lot. But their respect should not be imposed on them. It should be earned, remember that. Please do that. There is nothing to show off. This student one day, he may be even better than you. And you may have something to learn from him. He will always have, and try to build a relationship that even if he knows more than you, he should respect you because you gave them the spark to learn. Please remember that. And your job is to get more works done, inspire more students, only give the new ideas. Or you inspire them to come up with new ideas. Take the judgment, you need not take the judgment with you, but if you help them, they become very happy. If you are always aloof, so it's a fine balance you try to strike. Please do that. And those who are students, never, my honest request to you, never ever go against the teacher. And if he is doing something wrong, you have the intelligence to tell him, sir, is it not better to try the other way? Not saying that, no, I will not do it. Okay? One of my students, he said, no, sir. I told him in chatter, the cutting force and displacement, they lag each other. When the lagging becomes too large, chatter takes place. So the student didn't believe and he tried to disprove him. His results show that what I say is right. He still said, no, it doesn't. So when final exam came, I was waiting because we have another examiner, I'm the supervisor examiner. The examiner told me, Rahman, how much I should give him? I should know, I leave it up to you. He should fail. I only said, sir, brother, Prof. Ni, don't fail him. So he gave him 50. Now, we can vet each other's number because we sit in the meeting who gave what. If I give 60 or 70, he will catch me. Hey, guy, you said don't fail him and you are giving him 60. I also give him 50. 50 is pass mark. One day I met him in the bank. He said, sir, how come you gave me 50? I said, hey, believe me, your examiner wanted to fail you. I requested him to give me 50, so I gave you 50. I gave you 50, otherwise you would have failed. So, and I've seen in my life, only one student in my life so far, I'm happy to say, not because of me, because of my co-supervisor, the student misbehaved with me. He said, why don't you control your co-supervisor? I said, no, I cannot. He's independent. So the student, I tried to console. The student really misbehaved with me. And I pray to God to save her, but she's suffering. So never ever go against the supervisor. My honest request to all of you. 3 persons in this world are selfless. Who are those 3? Parents and teacher. Whole teacher, you bring them in one. Parents and teacher are selfless. If any selfish person comes for teaching, he should not do teaching. At least research he should not do. So never ever dare to go against them. And build the relationship. Nothing else will help you when you are on your own, but their blessing will help you. Again, the question is whether you believe in blessing or not. I ask my children, why do you good jobs for others? They say, Sawab is a Muslim. I said, have you seen Sawab? They say, no, we have not. Then, how do you believe it? What else? He said, we feel good. I said, that is Sawab. So, that means same thing, and blessing is a great Sawab. So, I'm not trying to be religious, but I try to explain that it doesn't matter what religion you belong to, but never ever go against your parents. And if any student or a teacher, any child goes against, don't give up. Talk to him, explain him, because you're the closest friend of him. If you lose the connection, partly you should be blamed for it. Okay? I think I'm going too much out. I think that these things are necessary, those who do not know it. Let me go back. So this haunting continued. I gave this work to, his name is, this Rahman is different Rahman, M.A. Rahman. It's not M. Rahman, it is Muhammad Azizur Rahman. Okay? And Unkeng Soon, because Unkeng Soon was, and Unkeng Soon became my colleague, so I allowed Unkeng Soon to guide him. So I brought him in. This is me. How Professor Venkatesh came in, I will not tell you. Because he likes me very much. He was in one of the institutes in India, very famous institute. He joined NUS. From the first day, I don't know why, he went to the airport to fetch me when I came from Japan to join NUS. So because of that and because of so many things, he was my wonderful guide. And I came from industry. I was in Makino, working there. From there I came to NUS because my father wanted me to teach and show him that I'm a teacher. I did my PhD. And what Professor Venkatesh told me, Rahman, believe me, publish or perish. But you should publish good paper. Okay? But he's very old now, he's close to 90. But we have the fraternity of CIRP. So 1 year, but he's in USA, one of the universities. He doesn't have a good research students. 1 year he wanted to go to CIRP. He said, Raman, I want to go to CIRP. And you will have to have a paper to get a lot of privileges. And let me stop it there. So I said, fine, I'll put your name there. I respect him so much. But he's a wonderful person. Okay? I presented the paper. All the details you don't need. So, modeling of the combined, now, what Wun Keng Soon did is only edge radius effect, A by R. Correct? Now what Aziz did, he brought in material behavior, microstructure of the material, hardness of the material, and all these things he brought in. Because I told him, do something new, and if you consider the hardness, maybe there is something new. So he believed what I said, because he was in the industry for 10 years, he lost touch with the academic life. I brought him forcefully because I wanted him to do PhD, and so I asked him to study the material behavior. So combine microstructural and cutting edge effect. So he added microstructural effect on cutting edge effect. He compounded them together and saw the behavior. So this one we have already discussed. I am not going to do this again. So this is show all these things. Okay. Now this one we have discussed concentrated shearing here at this region, and beyond that here material ploughing takes place. And in between what is going on, concentrated shearing is this, and when chip thickness is small, we got the extrusion. This is already established. Then he wanted to explore other possibilities at this A by R, on top of A by R. Okay? Extrusion-like mechanism was established. So we started with primary study that rather than going for very hard material, we took soft materials, magnesium, three materials, magnesium, brass, and aluminum alloy, to see their grain size is different, their hardness is different, how it affects the critical chip thickness in ductile mode machining. So whether it's the grain size, whether it is the hardness of the material, so he brought in that factor. Okay. So now if you look at as this is magnesium alloy. So magnesium alloy, the critical chip thickness at edge radius of 0.7, we get the minimum best surface finish. Correct? So the material hardness A by R, critical A by R is 0.7. When it goes to for magnesium alloy is 0.7, softest of the lot, and for brass it is around that 0.4. For extrusion, extrusion means best surface finish. For aluminium it is about 0.3. So yeah, okay. So as the hardness increases, this critical A by R becomes smaller and smaller, correct? As the hardness increases, A by R becomes smaller and smaller. So definitely material property has an effect that was established. Clear? So from there he started his journey. So he found that extrusion, a different extrusion range for different materials. Once it got established, he said, sir, I have got it. Shall I get my degree? I said, no. You will have to go for modeling, you will have to go for analysis, then only we will give you the degree. So this is the behavior, magnesium alloy, and now magnesium alloy grain size was 126 micrometer, and for copper or glass it was 35 micron. The color is wrong. This is for aluminum, it is 27 micron. Okay? Here something more can be done. I'll try to find out whether you can do something on this further. I will not tell you what it is. Okay? Homework. Follow me next, what is going on. So this is grain size. Okay? So that the threshold A by R increased with the increase of grain size as well as hardness, correct? So two things have been established. So now we can conclude that material microstructure influences the extrusion-like finishing. Whole thing he re-established, including bringing in the material structure in it. Then something new he needs to do. So cutting edge related effect, material hardness established, correct? Starting from magnesium, and then copper, then aluminum alloy, then this value steel which Unkeng Sun has established. So he didn't do experiment on it, he included this to make the graph look nicer. So again, different extrusion shown for different material hardness as well as for grain size. To make sure that grain size affects it, what he did, I'll tell you later. So material hardness increases, cutting edge effect also increases. Material hardness decreases, edge radius effect increases. Okay? That means harder the material, smaller is A by R, concluded. So combined effect now. So he tried to combine these two. Now look at it carefully. Microstructural effect A by R, he is bringing in the effect of A by D. D is the grain size. Okay? R is there, so he brings in A by D. Sorry, did I miss anything? The combined cutting edge and microstructural effect to have a better understanding of the mechanics of surface finish. So, but however little was known about it, so he wanted to find out whether he can get a new target was there. Usually varnishing is applied separately on machine surface to improve the smoothness. But if you do for varnishing separately by polishing and so on, the form error comes in. So in this study what he tried to do, investigate the varnishing effect through this study. So then it comes the boundary condition. What we need to know about varnishing. So he found out these are the factors we should analyze. We should analyze the material flow stress, analyze the specific cutting energy, analyze the chip morphology, machine surface quality. So he's set his boundary condition. So this way, to reach your target, you will have to think what are the conditions you need to study. And then, once you know what you need to study, then try to find equations, which equation will give you what factor. And then bring them into one umbrella, do finite element analysis or do experimental analysis and establish it. Experimental analysis, if it is fine to establish your assumption, prediction and both the graphs meet each other, fine, acceptable. And the arguments are very convincing, people will not ask for finite element analysis. But I was asking him, he said, sir, this is my fourth year, I have 2 children, I need to go to the industry to work. Can you help me to get it? I said, well, I can allow you to submit your thesis, very convincing, no doubt about it, but I want to test it not by finite element analysis, but by CIRP test analysis. What is that? Let me submit the paper to CIRP. If they unconditionally accept it, that means I'm demanding too much. So very reluctantly said, sir, yeah, please, let me take the challenge like a bet. They submitted it and paper was accepted without any argument, without any question. So I said, okay, as commitment you get your degree. So I will not ask any question now. I'll see whether you got another research project. He said when he followed it to establish analytical framework for combined effect of material microstructure and edge radius. So on edge radius he had to put again effect of edge radius on microstructure. That is the thing. Simple thing. Simple but very innovative and new thing. No research is difficult. Every research is very simple, if you can analyze the causes and to get the effect. Please remember that. If you initially think it is too difficult, like I'll show you the example of how to extract, how to drink the juice from anar. I will not tell you the solution. Okay, so what he did, he took the help of surface layer modeling, dislocation modeling, and based on grain size, crystal plasticity, and chip thickness. So all taken in care. He took the help of flow stress analysis model. This is the equation for flow stress analysis. So he started from analytical equation. And he had to spend a lot of time to get the proper equation. First of all, what equation to be used and where to get it. And once you know which equation to be used and where to get it is very simple. You can get it. Libraries have it. And you have, I'm sure you have access to international libraries. Any library in the world you can access. And for micro nano machining, simplest library so far, I think, I hope I'm not over-claiming NUS library is best, because all my theses are in NUS library, all my student theses, and NUS has free access to all PhD and master's work. You can get them anytime, any you want. Just if you forget the name of the student, ask me, I have the list with me, so I'll tell, okay, go to this thesis, search the NUS library. Okay, then all the values, what are the parameters you need to investigate, it is there. Microstructural effect, D is the diameter, though it is not a spherical thing, but assume it is a spherical thing, D by TC, critical chip thickness, Smith and Taylor factors which is needed to analyze the equation, which is M and small m in the equation, small n and capital M, and critical resolved shear stress, RR or eta R, half pitch coefficient, again you get it from the reference, average misorientation angle, theta. Okay? So from all these, you proceed. Now, things we need to critically think about it with a spherical indenter. Imagine that we're cutting is a sphere. So you imagine it is a spherical indenter. What will happen? Plus material will flow away and piling up will take place. It could be plastic, it could be elastic. And here you concentrate on both, then material pile up in spherical indentation. This is the creative part here to think of. Then fine scale material removal in ultra precision machining, because your chip thickness should be low, depth of cut or chip thickness, whatever way you term it, it should be low, okay, small. Material pile up, cutting edge effect, and whole thing is there. First of all, when you press the tool, so this is your contact depth when you cut it, and this is pile up on both sides, and then from there you calculate your specific cutting energy U based on all these geometrical figures given. Okay, it's a combination of an equation bringing in geometrical factors. You can say all these are geometric equations. Fundamental equation supported by geometric equations. Now come to the results. Equations I am not analyzing, not time spent will be unnecessary too much. Okay, and if you look at cutting edge effect, okay, considering the cutting force and thrust force, what Un Keng Soon did, following his results, he found out as the material properties changes around, depending on what material you are talking about. If it is aluminum alloy, it starts very late, it is hard, you can say around 0.4. When it is magnesium alloy, it is very high, separation starts earlier. When it is brass or copper alloy, then your range is about 6.6, 0.4, around within this range which we discussed earlier. This perfectly satisfies. And then bring in thrust variant. And if you bring in microstructural effect with cutting edge, then same thing happens for magnesium. Again, it is very high. For brass, again, depending on the grain size, it is low. Okay? But specific cutting energy, as you go thinner and thinner, specific cutting energy is very high. So here you see dominance of microstructure effect. Okay? So that way he connected chip thickness TC, and it is much lower than grain size. If you are exceeding the grain size, you may end up getting crack along the joining line. So that means, please remember, you are cutting grain. Now, if you are cutting grain, your energy level changes. So that part we are not considering at all. But we are just giving it one term, specific cutting energy increases. So these are about different grain sizes. So combining these two, specific cutting energy increases as your chip thickness decreases, and it is different for different material. Okay, magnesium alloy is the highest specific energy, followed by copper or brass and aluminum. So A by R basically should be less than 0.2, and at that point, around 0.2, it drastically, specific energy, cutting energy drastically increases. It starts earlier depending on the grain size and material hardness. Now, to see this dislocation effect, you can take the picture, but all these lecture notes are available to all of the participants. Am I right, Prof? Yeah. But PPTs, you can't keep a copy? Yeah, I'll give the PPT copy of all the slides. Some are hidden just to maintain within time. There are plenty of other slides which may be very useful. All the slides will be given. So try to have an access and use them. Feel free to use them. And anything new you find, you just let me know. Okay. To see the grain size effect, on the same material, one particular material, what material? Grain size of aluminum, we changed by heat treatment. We changed the grain size, and average grain size for these is 216, very large. And for grain size for the same material, we changed 53, another is 40. So just to see the grain size effect on same material. And orthogonal experiments, assuming A by R less than 0.2, and flow stress analysis. When we analyze the flow stress, we found a straight curve for all the materials. But when we brought in the cutting edge effect, you see flow stress 0. When the flow stress is 0, beyond this point, tensile stress is taking place. Below that, compression is taking place, correct? So this is tensile, and beyond this side is compression. So that means if you can maintain compression, crack will not generate. Exceed to that, go to tensile, crack will generate. Okay? So bringing these two together, you'll have to try to maintain, this material dislocation taking place within compression zone. Now you see, this interesting thing is that around that, within this, in a very short range, there is changeover is taking place. For different range sizes, this is the changeover range. So when you consider the combined effect, combined microstructural effect and cutting edge effect. Now let us see the details of this zone. So this transition is taking place from tensile to compressive or compressive to tensile. And important thing, we found a changeover zone. Now, we have a particular case of experiment when the edge radius is R 12.6, which is lower than any grain size. All the grain sizes we tested, it is lower than any grain size. Cutting speed was 100 meter per minute. A by R was around 0.2, and we did the experiment for different materials. A by R 0.2, aluminum alloy, copper alloy, magnesium alloy. And when the edge radius A by R is very, very large, that means most of the energy is spent for taking care of specific kinetic energy, hardly any material removal was taking place. You see the chips, which we do not want. Correct? So we do not want this type of chips, we want this type of chips. And when A by R is 0.1, you see, lines are very clear, but some crack is taking place. Fracture is taking place. Okay? So we analyze the chip morphology, and this was observed by Professor Nakayama long time back in Japan, and it matches his two types of chips. Okay? And he termed this as chip type 1 and chip type 2, but in between we got another type. We call it rifted chips. Perforated chips or rifted chips, yeah. Then here we get complete chip. A by R is greater than 0.1, greater than in between these two. And rifted chips or perforated chips, when A by R is 0.01 to 0.1. This is the zone where we need to concentrate. And when it is A by R, A by R is 0.01, then we get this one. So we need to concentrate between 0.01 and 0.1. This is the zone. If we go further, for magnesium alloy, and we did experiment 3A by R. 3A by R, A by R 0.1, A by R 0.05, A by R 0.01. And machine surfaces, magnification 100, 250. If you see these three things, and this seems to be cleanest zone. So this zone was identified, and we say identification of superior finishing zone, variation of magnesium alloy machine surface finish. For magnesium alloy, this is the graph we got. So this is our extrusion zone. This is the zone, changeover zone we got, which we termed as varnishing zone. This is the best surface finish we got. At this zone, we call it best surface, area of 58 nanometer. It's a varnishing zone like this. This is for magnesium alloy. Did we do a further experiment? And if we take all these varnishing, like finishing For aluminum, magnesium and copper, all three, these are the graphs. This is for aluminum alloy, this is for magnesium alloy. This A by R changes, and this is for copper alloy, which is brass. Okay? But these values exactly do not follow the predicted trend, but quite close in the region. Now, if you look at the improvement, for surface finishing, as you saw, two zones. For shearing, based on fundamental metal cut equation, for aluminum alloy, we get surface finish of 163.79 nanometer. For magnesium, best surface finish, magnesium 162, copper 218. But by extrusion, we have an improvement for all these three alloys. For aluminum 111, magnesium 83 and copper 60. But if you go for varnishing zone, the new zone, you have a significant improvement of surface finish, aluminum 62, magnesium 58 and copper alloy. And you see the drastic improvement in surface finish. And improvement percentage is up. Percentage of improvement, shearing to varnishing 61%, 83% and 86%. Shearing to extrusion is this percentage, and shearing to varnishing is this improvement. So this is the new zone. In varnishing, material does not get pushed out, material gets suppressed. But you will have to maintain that chip thickness. So what we did is combine microstructural and cutting edge effect, which governs by the transition from tensile to compressive stress. And high compressive stress at the fine cutting edge, cutting magnitude, responsible for drastic increase in specific cutting energy. Please remember that. High compressive stress induced on the machine surface, favorable for varnishing process. So specific energy, cutting energy, high specific energy helps in getting the varnishing. Discovery of changing region for aluminum, magnesium, copper alloys, and it has been irradiated. So the new region has been established. Varnishing or varnish-like finishing mechanism is in ultra precision machine. So now CIRP has accepted two new regions. So shall we continue with, so in the meantime build up your own research. Shall we continue? Okay, diamond very quickly I'll finish. No, I have few things to say. Correct, I should not quit. Okay, I do not want to extend it for another day on diamond turning. Correct? Let us finish it. I will try not to rush if you are not hungry or bored. Okay. Now, conventional diamond turning, I think briefly I discussed, it is very difficult to get free-form surfaces, which is not true, and difficult to obtain mirror finish on brittle material, which is not true, not economical. Conventional diamond turning, but it is true, but conventional diamond turning, if you come up with new solutions, then all things can be done. So free-form surfaces cannot be machined in conventional, and brittle material cannot be machined, and it's not economical, fine cutting depth, because the tool wear is very fast, short tool life, and steel cannot be machined. So all these problems, steel is the most important material to machine, or most widely used material, so we should get rid of this problem. How to get rid of it? That comes first tool servo and slow tool servo. Okay? Now, as I explained many times, first tool servo is the tool is moving very fast, and slow tool servo tool is not moving at that fast, and the slow tool controls the tool post is moving. Okay? So this is done by special attachment on the z-axis. First tool servo. In first tool servo, tool movement lower amplitude, please remember, higher frequency, 500 to 1000. Again, it's not ultrasonic vibration, 20,000, 30,000. Usually first two servo, amplitude is small, but frequency is about 1000 hertz. For discontinuous surfaces, for example, lens set array, micrometer and so on, it is used for that. Slow tool servo, tool movement at higher amplitude, very large amplitude, because tool post is moving lower frequency, 2 to 70 hertz only. For continuous surfaces, non-symmetric surfaces, free form, all these are meant for free form. Even a 2-axis machine you can do it. So this is an example of first tool servo detail, and here in the tool post we have used a flexion mechanism which controls within that flexion mechanism we have a piezo actuator. It is mounted behind the tool which controls flexion mechanism, bends and straightens, bends and straightens. That way tool tip position changes, and that decides the amplitude. This is the mechanism. Here is the tool post. Tool is moving on the surface along this axis. Okay? And all these details are there. Tool is moving along this axis, and while it is moving, the tool post below, you see the green thing, it is the piezo actuator, and piezo actuator is mounted on flexion mechanism so that with the expansion and contraction of the piezo actuator, the whole tool post mechanism can move up and down. That way its tip position changes, tip distance changes. All the details are there. And more details are shown here. Okay? This is the tool post. This is a small lathe we developed, and which was used for experimental purposes. And this, okay? So the tool is moving along this axis as well as along this axis. So z-axis whole tool post can move, and tool can also move. In x-axis tool post is moving. And this machine we developed has two features. One is, when it is moving, we can detect the position of the tool post, the whole tool post as it is. So that gives the form error. If the tool post is moving in a wrong way, zigzag way or inclined way, then it can be detected. So displacement of the tool post can be measured, straightness, so that way horizontal straightness of X stage can be done. So that takes care of form error. Okay? It has two. One, it takes care of form error. And when we machine two materials, brass and aluminum, we get this error. And waviness, straightness, all can be measured. So when we measure, we can measure the straightness, and the first tool servo has servo control, and it measures the surface roughness. Second graph was actually surface roughness. This was the surface roughness. Yeah. So that way you can measure the surface roughness as well as straightness, and you can compensate both. And the surface roughness, straightness is measured using a capacitance sensor. With a reference surface, capacitance sensor takes care of the measurement of deviation. Then you can compensate. You see, this is the result, this surface roughness, when we apply the feedback control, and the error is almost zero. Right? So this is the beauty, using first tool servo, controlling both form error and roughness error, and you can get the best accuracy. You can bring it to nano accuracy. And so without first tool servo and with first tool servo. And you can have all these features, flat surface on flat surface, you can have lens array, pyramid array, whatever you want. These are simple examples. You can have more and more complicated ones. So much of complicated things you can have using first tool servo and slow tool servo. Okay? Am I talking too loud or low? Voice is okay? Microtongue examples. Now, so when we bring in vibration, ultrasonic vibration device, ultrasonic vibration device, it is done at very high frequency and amplitude can be varied. So it could be 1D, which is conventional ultrasonic vibration device, and it could be 2D, which is ultrasonic elliptical vibration device. Now let us discuss their advantages and disadvantages. Ultrasonic vibration device, one-dimensional, it is just moving in one dimension, hitting the tool at the same point, and tool wear is very fast. And because the cutting force is large. When you move in elliptical path, I will show the details, it contacts from here up to the stagnation point. After that, it pulls the tool behind, cutting force is significantly low, and you can machine any material. With this ultrasonic vibration device also you can machine steel, but the problem is tool life is short. Whereas if you use elliptical vibration device, your cutting force is very low because and tool wear is very less, heat concentration on the cutting tip is very little, so tool life is very long. Chip thickness is very thin because the cutting force is, chip thickness is very thin, so cutting force is very small. From both the points, elliptical vibration device is much better solution to have higher, longer tool life, better surface finish, and almost with zero tolerance. So let me talk little more detail about this ultrasonic elliptical vibration device. Same PZT, piezo actuator, but here the combination of two resonant mode. One is second resonant mode, which is in the longitudinal mode, and fifth resonant mode in the bending mode. So combining these two, you rotate the tool in elliptical path. And this amplitude A and B in two axes can be varied, very controlled depending on, and you can determine your maximum metal removal rate. I will not drag you onto this. So a tool is set up with the device. Okay, this is the device, and so this A and B can be varied. Then the size of the ellipse, whether it is vertical or horizontal, you can control it. That way you can control the metal removal rate and surface finish, everything. Tool moves in elliptical path. Please look at this, during return paths, the rake face of the tool pulls the chips, thereby reducing the friction and thus reducing the effective cutting force. And cutting force is very less. All these details I will skip, equations are there. And tool tip contact time is very short, which is time of cutting and free time divided by the total time. This is the device, and it is cutting star works. Processing condition, cutting depth is 10 micron, feed rate 20 micron and cutting speed is 1 meter per minute. Roughness of the surface is 5 nano. So you can see you can machine steel. Now this one, I don't know, I hope the video will work. It may be interesting to you. It should be working today. Yesterday I saw it is working. How come? Huh? Why is it? This is for chip. Actually, mechanism was in that. I will bring that video later because I have the original thing. So this is chip formation. You look at it. Okay, give me some time. I'll show you the video. I know how to do it. Okay, now let me go back to this. Chip. If you look at the analysis of the chip, it's conventional cutting. Chip thickness is constant. old-fashioned vibration cutting mechanism, chip thickness is constant. Then if you go to elliptical vibration cutting, you see chip thickness. So it has been changed from conventional to apply this elliptical vibration, chip thickness becomes much thinner. Okay? In elliptical vibration cutting, their shear angles is this, it is very large, and chip thickness is very, very small. And we machined tungsten, and I think no other process you can machine tungsten. No other process I can guarantee you. Using elliptical vibration device, you can machine steel, you saw the example earlier, you can machine tungsten, titanium, anything. This is the beauty of it. So tungsten using elliptical, ultrasonic elliptical vibration cutting, using PCD. Beauty is using PCD, can you believe it? And if you look at the result, RA is 3.61 nano. Yeah, this is another graph. This is conventional cutting, conventional ordinary cutting, and elliptical vibration cutting. Okay. Micro cutting, SCM. And all these comparisons are there. If you compare conventional cutting and conventional ultrasonic vibration cutting and elliptical vibration cutting, if you see for cutting force, for conventional diamond turning, cutting force is very large. For ultrasonic, it is low, and for elliptical vibration, cutting force is extremely low. Tool wear, conventional cutting very high, ultrasonic cutting low, and for elliptical vibration very low. Tool life for CC is very low, conventional cutting. Tool life is high, but in elliptical vibration cutting it is very high. Chatter suppression, no mechanism to suppress chatter. Chatter suppression is satisfactory, highly suppressed chatter, because chip thickness is very thin and cutting force is very low. Surface finish, below 1 micron, below 0.1 micron, here also below 0.1 micron. Shape error, very high, medium, and shape error is very low, all related to cutting force. Speciality, effective mainly for ductile soft material, and for steel you cannot use it. Considerably effective for difficult to machine materials, and very effective for difficult to cut materials. Therefore, ultrasonic vibration cutting, especially ultrasonic elliptical vibration method, is very much favored to machine difficult to machine materials. So these are some more things, and ultrasonic elliptical vibration ultrasonic vibration cutting, you can get really smooth surfaces. These are other factors, how to calculate the maximum A and B. I am not going to drag you. Based on that, relevant machining parameters you can determine from this equation. Not elaborating from there, you can control A and B, okay? And you can get your maximum critical values. I am not putting you there. Oh, some results are here actually. Machine surface by ultrasonic elliptical vibration cutting, the material is mirror surface finish, NUS is reflected on surface, material is tungsten carbide, applying ultrasonic elliptical vibration cutting, and technique 4 micron nominal depth of cut using PCD and single crystal diamond. Depth of cut is 6 micron. Surface finish using PCD was 7.5 micron RA, and single crystal diamond was 4.6 micron, depending on what you want to use. If you want to use PCD or single crystal diamond, this is the variation. Okay. So remarks, conventional technique is not suitable for machining sintered tungsten carbide. Ultrasonic elliptical vibration technique is capable to obtain mirror surface finish at higher nominal depth of cut. Applying ultrasonic elliptical vibration technique, even inexpensive PCD tools can give you cost-effective reasonably good surface. Choice is yours. Some of the examples of machining. Thank you very much. Any question?
Sir, I have few questions.
Yes,
One
sir.
is this RA and SA. Now, after getting this Alicona,
Yeah.
aerial surface roughness is coming in picture. Aerial surface, SA. Instead of RA, SA is also we can get it. Aerial surface roughness. What is the other name for the aerial surface? 3D surface roughness. Are you getting me? Instead of RA, SA. Aerial surface roughness, or it's known as 3D surface roughness
Surface roughness?
of the area.
Yeah.
SA.
SA.
That is the basically average of all peaks and valleys in 3D surface.
Yeah, it depends actually. RA is good enough. Now, if you need to be very specific, there are other parameters as well.
No, sir, because these techniques has come recently.
Yeah.
Maybe other people, Ragesh, or you can say about
It
that.
takes care of area.
Area, is it better because what is
SA
that?
could be better because RA is along a line.
No, but still we are not seeing that much papers coming in with the essay.
But
If you look at the latest papers, most of people are using, I guess,
I don't know, SA should be more useful, yes.
Again, for the historical reasons, we know, I mean, the surface roughness measurement, it started with stylus-based measurements. So it was a line scan,
Line scan.
and that was the more effective and economic and straightforward way to get information about the surfaces. Now, when we compare RA with the SA is very good area surface roughness, wherein we try to, and it made possible because of the optical instrumentation, because capturing the area and getting all the data is now just a matter of seconds.
As if like camera is observing.
Yeah, so you can capture all the information and you do the signal analysis and you get the SA values. So it is doing for the given area. So it is much more faster. Now utility of it, coming back to it. Now we can segregate the processes. For example, if you are having a single point cutting tool operations, let's say turning, facing and all, the SA value is not going to give you much more information. At most what we can do, you can have the RA scans, maybe along the cutting direction and orthogonal to it, and that should be enough to give you the surface information. But when you go to the complex processes, for example, if you take the EDM, which is much more random in two-dimensional. So in that case, SF is going to make a much more, it will give you much more information. So that is one take. The other thing is that when you go to the application will tell you which value they want to have. Let's say you want to have the bearing surface. Okay, so they will have their own specific standard. So that will be dictated by what application you are going to use. But as far as process engineer is concerned, and you are trying to understand the process or the surface quality, majorly I would say that if you have some process understanding, it's a single pointing, we know the kind of a lay or the pattern is going to be expected. If it is just a two-dimensional one, you don't have to go for the SA and complicate the things. And the third point is standards. Now most of the standards, of course these standards need to be revisited again and again based on the available information. So the RA parameters, the single dimension parameters are well defined. We know this roughness values and all, they are highly sensitive with the kind of a sampling lengths. So throughout the experience or the industry inputs, the RA values, single dimensional values, they are quite well defined. So when it comes to the SA, things gets little bit complicated. So thumb rule is, I mean, if your process is more random in nature, maybe grinding or perhaps the EDM, then in that case, it makes sense to look at these SA parameters. Yeah.
Just to add to it, I feel SA may be useful when you are in doubt whether the tool were caused surface accuracy deviation. You started from one end, went to the other end. By the time if the tool wears off, then SA may be useful because fine tool will give one surface finish, rough tool will give another surface finish, if it happens at all. Yeah. But of course, in random processes it may be useful, very useful by EDM and other.
No,
Here, the beauty of, so just to add, beauty of tool-based machining, not, these are conventional machining processes. You use a tool to cut material, the process is predictable. What is the surface finish you will get, or what is the form error you will get based on the machine deviation. Whereas discrete processes like grinding, EDM, and all these things, quite non-deterministic process, especially grinding and EDM. But EDM, again, we are trying to bring it to be a deterministic process. So assay could be very useful there. Yeah, please.
Well, sir, because Alikona was saying that all these are standardized, all these standards in metrology is there, but still I was not seeing that much papers. That's the question. Okay, now, sir, next question is regarding that papers, the CIRP, because we all know that annals of CIRP, even IIT Kanpur onwards, I heard that annals of CIRP is one of the best journal. Yeah. If you get a publication there, it is one of the best journal. And one of my research student, he went for a PDF in Germany. He got a CR paper last month. We like to know what are the procedures.
Okay.
I know that some membership, it has to come along with the member and all. And then JSME also, that's another one, Japanese Society of Mechanical Engineering, ECTC for Indian students to get publications in. So annals of CRP as well as JSME.
Okay. CIRP, my experience, I can share with you, I think I'm right. CIRP, what they look for a breakthrough. You may do an extensive work on something which has been done, straight away it is rejected. Unless the old work was a junk, they accepted, maybe they accepted or not, that time that was the best paper. Now the level has gone up so much that original paper has become irrelevant. So you have done something great. For instance, machining. They're tired of machining papers. If they get 100 papers, hardly 30 papers get accepted. I mean, giving the ratio, 1/3 papers are accepted. So, if there is machining, if they would say, oh, Unkyung-sun's paper is a machining, rejected. No. In machining, he has done something extraordinary, something new, so they will accept it. So they are looking for new ideas. And idea alone is not enough, it must be thoroughly analyzed, established, above debate. So it is substantiated by experiment, new idea. It should be a complete thing. Most important thing to start with, it must be new, something, some breakthrough. So please remember that. Some people say, oh, PIP, what is this paper? Is it so big? The big thing is that it is something new. All these new, in manufacturing, if somehow is related to CIRP, and you need not be a member of CIRP, you need not be a corporate member or fellow member or corresponding member, need not. Anybody can submit, only condition is that you will have to go through a member.
It should be a call.
Yeah, member, it should go through a member, and the member number will come as number 1. But problem of member, every member wants to submit a paper. If he doesn't have anything to submit, then by now we know who doesn't want to submit paper, who does not want, or he doesn't have the research cohort to have a paper worth publishing in CIRP. Last year I had 3 papers to submit. So 3 papers to submit, what to do? And 3 students, 3 or 2, 3. So I told, and moreover I have my co-supervisor, and I told the co-supervisor, he is not also a member. I gave him the first preference. Which paper you want to be in, to be submitted in CIRP. So he said, this paper I want. Okay, I'll tag with you, because I want him to be a full member. Otherwise he will think I remain full member forever. I tried many times, but none of the papers he strongly contributed. And I always, if he doesn't contribute, I put the student as the first author. Anyway, so he said, I want this paper. So he could become the first author, submit the paper. And then another paper, I don't know whether the co-author agreed to put him as first author or not, but at least he was there. And then another paper I wanted to submit, So I had to, either I'll have to look for another person to submit the paper, because I cannot put my name in two papers. So I got Professor Venkatesh with my student to submit the paper. And another paper, I put his name, I also put my name as well. Otherwise you would say, knowing that paper quality is not good, I am not putting my name, which is not true. Both the papers are very good. And then Venkatesh paper was accepted. So I wrote to CIRP that I submitted two papers. In one my name was there, but the paper is not accepted. Another paper I submitted, my name I could not put because this is. They said, well, if the other paper is not accepted, you ignore that paper and bring your name in it, so that I can satisfy both the parties. Because my student would love to see my name, that I am there in the paper. So that way, submitting two papers, one without my name, one with my name, one accepted, another unaccepted, but I could swap my name. So it must be submitted through. Professor Venkatesh did not submit any paper that year, so we just took him in, paper was in, and I put my name in. So there are many retired and honorary professors, those, they can submit, they have the right to submit, you can submit through them. If you want, you let me know. Last year one Chinese guy wanted to submit a paper. I again wrote to Professor Venkatesh and he was happy to sponsor. I told them the paper will not be accepted. The author was from Fudan University in China, very famous university. But he said, no, definitely it will be accepted. But I knew that similar work has been published, so, but his paper was rejected. So it must be original, something original, breakthrough, substantiated, all three conditions. And India has a great scope. Not, if I am not wrong, not a single Indian member is working in India. There are Indian members, and they are working in mostly overseas, and so they know America. In America and Europe, the quota is full, and each country cannot have more than 15 members. So every country is full. Japan, worst case is Japan and USA. So those who are working in Japan, they use Indian address to become member. Working in USA, but originally from India, citizenship doesn't matter. They say, I'm submitting my name because I'm an Indian from Indian quota. So India has huge 15. Singapore being such a small, we are already 3. And because Professor Venkatesh is using Singapore quota. So 3, now we are 4.
So then the JSME, Japanese Society of Mechanical Engineering, is it easy to get publication in that?
In
JSME?
JSME. JSME, not easy, very difficult, but no benefit of submitting in JSME. JSME problem is this journal, though it is very good journal, but its international circulation is very poor. JSME is much harder than ASME, but international circulation is low. For your own satisfaction, I think Japan has the widest readers, in manufacturing. I can guarantee. So JSME is extremely good journal. ASME is good, but in America it is highly rated. Internationally it is not. I don't know why. Internationally, MTDR journal UK is after CIRP. Machine tool and manufacture, yeah. Machine tool and MTM. Previously it was MTDR. Anyway, so that journal is highly cited until CIRP came in. I think they are fighting there. And next journal is Journal of Material Processing Technology. It has moved very fast. These 3 journals are very good. After that comes ASME, JSME, and so on.
Okay,
And I will, when I discuss about how to write a good journal paper, I will discuss all these things. What a good journal is looking for.